Colleagues, a very warm welcome to our seminar series on Science for the Green Economy. So this is our seventh seminar on aspects of offshore. Can I introduce myself? I'm Simon Pollard. I'm Pro Vice Chancellor for Energy, Environment and Agri-Food at Cranfield. We're delighted to welcome you on behalf of Cranfield and Herbert Smith Freehills, who host us in our seminar series. Our series is an attempt to bring to the green economy debate a strong technological management and legislative input. And so we've had a whole series of seminars, our last one being on green infrastructure, that really provide that sort of strong technological rationale to the green economy discussions. And we've got I think what will be a very lively evening for you lined up this evening on offshore wind standards, certification and litigation, somewhat provocatively termed perhaps. I'm going to introduce our speakers in a moment, but before I go on any further, can I make a shameless plug for our conference in January. Our Science for the Green Economy conference at Cranfield University, that's 50 miles north of London, for those who don't know us. It takes place in the beginning of January. It's very reasonably priced, I would hasten to add, but it is the focus very much on clean tech, start-up, jobs for the green economy, scale-up agenda, so very much in line with the government's initiatives on the green economy. The first day is a national debate on technology and governance. The second day is a specialist conference for early career researchers as well, so if you're looking to see some of the upcoming talent in the research side, do also think of day two. But to this evening, our speakers this evening are Professor Fergal Brennan. Fergal's our Director of Energy at Cranfield across the university's expertise. He's an international expert in offshore structures and is our Professor of Offshore Renewable Engineering. Professor Paul Leinster will be known to many of you as the former Chief Executive of the Environment Agency and now a Professor of Environmental Assessment at Cranfield. David Nitek is a partner here at Herbert Smith Freehills in the litigation team, and Julie Vaughan is our co-host, associate partner of the environment law practice here at Herbert Smith. So with no further ado, Fergal, can I ask you to give your overview?
Right, thanks Simon. So firstly, what I want to do is I want to set the scene. I think it's really important, and it's incumbent on people like me, and I also think on you guys too, involved in this sphere, to firstly examine the context. Offshore wind, yes, on a day-to-day basis we get involved in design, commercial aspects and so on, but what's behind this? What are we trying to do? I'm going to just show you firstly, this is if I plot CO2 over the past 800,000 years. We can see it goes up and down every 100,000 years or so. If you cast your eyes right over to here, there's something very unusual happening. And if I zoom in on that over the last few hundred years, and if we look at what is happening here, this is Victorian times. This is where the Industrial Revolution has started. This is up to the present date. So this is for the past few years, and we see it climbing above the 400 ppm value. And either later this year or next year, we will have an average value of CO2 at over 400 ppm. The last time levels of CO2 were this high, we had dinosaurs running around the planet 65 million years ago. This is indisputable as to what is happening. And we're going to hear a lot about this over the next few weeks in the run-up to COP in Paris. I take this very seriously, being a director of energy. 35% of the CO2 and the greenhouse gases are generated through the energy sector. It would be surprising to people to see that 24% is agri, 21% other industries. Transport, we might have thought would have been higher. It's not. And in the wake of VW recently, you know what? A lot of that's going to shift over here as we move to electric vehicles. Yeah. So this is really important stuff, and we've got to be mindful of what's behind this. We, whether we're lawyers, whether we're economists, whether we're technical people, we're pioneers. We've never been here before. And if we are to manage our way out of this, and we will do, it's going to be the engineers, the managers, the technical people, the people who are involved in regulation, litigation, commercial, that will get us out of it. Yeah? Right, and finally, I just want to say is that sometimes people say, oh no, we can never move and so on. Here's where we got our energy from in 1980 in the UK, or sorry, our electricity. Look at this, 67% from coal, renewables hardly there. 2007, coal was halved, and look at this gas has come from nowhere. Just over 5% in renewables, and here we were last year. Incredibly, renewable energy up to 19.2% of our electricity. Look at that terrible 29% of coal. We got to get rid of that. We either clean it up or we get rid of it. But the message here is, we talk about an energy revolution. We've always had that revolution. We have been changing all the time. So over a few short decades, we've shifted around our energy balance. We have a real opportunity here to continue to have a healthy, diversified energy mix. And as I say, Paris is coming up. We're going to hear an awful lot more about this, about the OECD, non-OECD countries and their roles and so on. Unfortunately, I think, and many of you here will agree, that the UK may be somewhat embarrassed with the way in which direction we're going in. China and the USA, Obama is keen on his legacy, I think will probably put us to shame. But this is a long-term movement, and I think all of us have a responsibility to understand what we're up to here. So let me just spend a few minutes on the science, engineering and technology. So I've got Big Ben on the left-hand side. I've got the Eiffel Tower at 324 meters on the right-hand side. This blue bit is where we started to go offshore. And you can see that only a few short years ago, 2002 and so on, these are the things, and these are the land-based ones that the NIMBYs, not in my backyard, complain about. And this is what we're starting to do offshore. And these are giants, true giants. Why do we want to do this offshore? Well, firstly, they're out of sight, so planning isn't such an issue. But more importantly, the wind resource is far better. The capacity factors are between 30 and 50% better offshore. I get 2 identical wind turbines, one onshore, one offshore. I will get up to 50% more energy over the lifetime from that offshore unit. We also can do things much bigger offshore. And the bigger, the better as far as this stuff is concerned. So what I want to do is I want to set the scene for some of the issues that we've had. And I call them issues, challenges. I'm not scaremongering. This is, as I said, nobody's done this before. Steep learning curve. So the fact that we may have had a few design issues or concerns or disputes doesn't surprise me and shouldn't worry us. But when we consider design consideration for support structures, those of you who may not have a structural or a technical background, the first item there is the primary purpose. And we'll design something, a wind turbine, to resist an extreme event, a 70 meter per second hurricane gust, for example. However, there's a whole lot of other things that go on. We've got maintainability. We have to design for maintenance. We have to design for installation and transportation. Very often we will put more stresses on something as we're getting it into place, as we're piling it into position, than during its lifetime. The Capex and Opex, so getting that balance right between not spending too much at the outset, so that we scupper the cost of it, but then also ensuring that something is fit for purpose or fit for service. Not a Rolls Royce, not too good, but fit, appropriate. It's got to be as good as it's got to be. No better, no worse. That's how we optimize. And hugely important is the environmental impact and environmental life cycle. Very topical at the moment. Paul and I discussed this before it started. China dumping cheap steel on us. What's the significance of that? The steel, in terms of the steel itself, it's virtually the same. But what is the carbon footprint of that steel from China? Where is the electricity coming from to create that steel? It's coming from a very polluting place, and we in Europe should really be thinking carefully about that. It's not the price, that's only one part of it, the economics. It's the totality of the impact. Same with PV, got to be careful. We put PV in our nice little middle class houses here in Europe, and what is it doing? What's the local environmental impact in the places where this stuff is made? Yeah. So we've got a responsibility, and we'll hear an awful lot about that in COP in Paris. Right. I just put this in because sometimes people ask themselves, why is Northern Europe, why do we have so much offshore wind? The UK has the most installed offshore wind capacity of any territory in the world. This is a depth map, seawater depth map. The red bits are the shallow bits, less than 40 meters. Look at this area. The blue bits are 1,000 meters. And those of you who like sailing like I do, I know that if I go into the Med, I'm in a couple of 100 meters of water within a half a kilometer from the shore. Yeah, that's why we have no wind turbines in the sea in the Med. Very deep, very unusual here in Northern Europe. So we started off basically getting land-based technologies, and again, if you like, forgive the pun, dipping our toe into it, into relatively shallow waters, and then developing at a relatively low risk. And that's why we're so good at it, and we have been so good at it, and we've got that advantage over the rest of the world, but only just. In terms of the different structures we have, most of us are dealing with these monopiles, the fixed foundations. But as we get deeper, we've got the gravities, we've got the tripods, we've got the jackets. And then once we get really deep, and we will have wind turbines in the Mediterranean, but they'll float. And we've already seen a number of floating demonstrators. Post-Fukushima, and if you Google Fukushima forward, you will see 2 trial devices, 7 megawatts each, huge wind turbines, floaters. And the Japanese have mobilized that program since Fukushima. Hugely impressive. So if we don't, keep the momentum going here, we will be overtaken. I want to talk about, so firstly, where we're up to. In the last quarter of 2014, 22% of the total UK electricity supply was from renewables, 12% from wind. It's extraordinary. Yeah. And we're talking about Hinkley Point at the moment, hugely, yeah, but nuclear is 20%. We are now today generating more electricity from wind power than from nuclear. How many people appreciate that? Right. So, but behind this pioneering success, and to the lawyers here, I've been very careful. This is all public domain stuff. We all know about a number of the high-profile disputes. But here are a few of these things. We'll see a number of these grouting issue. Chief resigns from the. This is a Greater Gabbard, I'm sure. Who do I see here is involved in that? I won't point you out. Anyway, simply, this is $500 million US was Greater Gabbard. At one stage, it was predicted that the repair bill was. What was that about? It was about trying to reduce costs, and Fleur, the contractor, thought that it could reduce cost by reducing quality, potentially, and going to China and getting stuff cheaply. And those of you who are involved in offshore engineering know that Mother Nature takes no prisoners, and you cannot put defective structures in the sea. They will be taken apart very quickly. Here we have similar guys again, and a number of them. And I think I'm almost there. You can see now that Fleur has turned its attention to China. And there's a nice one, certification vitally. Ross was supposed to come today, but he authored that. And it is important. And I want to move on now to why certification and standards, where they fit in. So, firstly, offshore wind structures are dominated by metal fatigue. I'm not going to give you a lecture on metal fatigue. Suffice to say that the components in here are the material's resistance to cracking, the extent of defects. Lawyers will say defects. Every engineering structure, every material has inherently defects. They're defective. That's why we're engineering structures. The extent of them is important. Stress on the environment. But fatigue, as a design, as the failure process goes, is not so bad. The worst kind of structural failure I could envisage is one that goes bang without any warning. Corrosion and fatigue, they're time dependent. They happen over a period of time. We have a micro or a nanoscale fracture. And what we can do with fatigue is we can go and we can look at it and say, right, oh, there's the crack, and we can quantify it, and we can model it. And we can say, right, don't need to do anything now, or else we can change our loading on it. And that's one of the big differences between an offshore oil and gas structure, where we can't do anything about the loading because that's based on the wind and waves. But a significant proportion of the loading on an offshore wind turbine comes from the machine itself. So I can choose in my car, I could have a very low fatigue life on my car if I ran down the motorway at 120 miles per hour all the time. It wouldn't last very long. With a wind turbine, I can do the same thing. I can moderate potentially its control system. So fatigue ain't bad as failure mechanisms go. And if you wanted to choose one, fatigue you can control and work with. And this is a plot that I've shown a few times, and I've forgot to put, I've borrowed this from Professor Sumi in Yokohama. And let's have a look at, firstly, the Capex is the black line, and I've got probability of failure on the horizontal axis. So I can put so much money into something, I could build an artificial island, so the thing would never fail. It would cost me a fortune, but the cost would be prohibitive. And at the other end of that, I could have a very, very low capital cost, but a high probability of failure, but associated with that, a very large insurance cost, maintenance, and risk of failure. So my total life cycle costs are somewhere here. And this is important, probability of failure. If I build an offshore structure and I want to put 80 or 100 people on board, we know that risk is the product of probability of failure times the consequence. So where I've got human life involved, the consequence of failure is large. So my probability of failure needs to be reduced. I cannot tolerate, and it will not be acceptable to have a high probability of failure if my consequence is high. My wind turbines are unmanned structures. So the industry and certification and the insurers are generally arriving at a consensus of a failure rate, a tolerable failure rate, at 1 by 10 to the minus 4, 1 in every 10,000. Whereas if I'm involved in offshore oil and gas, we have a target reliability of 1 by 10 to the minus 8, 1 by 10 to the minus 9, 100 million or 1,000 million. Okay? So, if I was to use offshore oil and gas standards to design offshore wind turbines, what am I doing? I'm over-designing them. Of course I'm over-designing them. I'm going to couple that with the fact that very few offshore oil and gas platforms on the UK continental shelf that have all exceeded their design lives have ever been decommissioned. There's only a handful that have been decommissioned. So that means that we over-design them in the first place. In order for us to get down to the right cost and to be cost competitive with fossil fuels and others, we need to be more clever. We talk about jackets versus monopiles. A few years ago, lots of people were looking at these as we got deeper. And however, myself included, a lot of people think we can get a lot more out of these things. They're simple. We haven't even tried higher strength steels yet. There's an awful lot we can do together. So let me just talk about standardisation. and we talk about the expense of the oil and gas legacy. So we have, if you like, inherited the standards from offshore oil and gas experience. Why? Because DMV and others hadn't envisaged that we were going to build these things 10 years ago. And anyway, they don't have a budget to go out and commission research. So what we've done is we've taken experience from manned high-risk installations. We're using fabrication inappropriate design standards that are 30 or 40 years old. The materials tests that were done on these things were done in the 1970s, 1980s. Now, if I need to reduce costs, I need to be clever about this. I cannot afford not to use the very latest in manufacturing techniques, fabrication, quality assurance, and so on. Any of you who've ever come to a manufacturing activity in Cranfield, you'll see phenomenal things. You'll see robots, automated welding systems, inspection, and so on. Unrecognizable compared to when oil and gas platforms were designed. So we need to get there. We have also got a very different cost imperative. The margins in wind are much, much smaller than oil and gas. I can be cheeky, and I can say if oil and gas have a problem, they just can chuck money at it. They've got deeper pockets. They whinge at the moment of the price of oil, but yeah. Right, so let's look at the advantages and potential perils of standardisation. The advantages of standardisation is that it affords volume services, expanded and therefore more competitive supply base, and the ease of regulatory and certification approvals. So that's nice. We standardise everything. We can say, on you go, let's get competition. We have an expanded supply base. The dangers are, however, that it can block the introduction of new technologies, can restrict the supply base to only those who are in the standard approved club, and can make incremental improval difficult and rule out radical designs completely. So we've got to look behind this. I give the example of Germany. We know that the German manufacturing industry, the lobby there, is hugely important, more important than the offshore wind industry. A lot of pressure on the big fabricators who need to get their shareholders to invest in new equipment and infrastructure and so on. And what do they need? They need to say it's going to be this size, it's going to be like that, it's going to be this colour. Yeah? That's not what we need in order to innovate. So in terms of the developers, the designers, the certification people, and in terms of UK or the world PLC, we need to empower the best brains to come up with the best designs to continue to develop. So there is a halfway house here. There's an important distinction, and different industries have different cultures. The prescriptive-based standards are go there, pick this up, rotate it through 180 degrees, put it back and whatever. Yeah, telling you step by step that this is what you do. And you need a prescriptive base if you don't have a great deal of competence. You have to micromanage, you have to tell exactly what needs to be done. With goal-orientated or target-orientated, you can simply say, the target here is to achieve this. Now, go off and use contemporary methods, reliable methods, and quantify, in terms of safety and so on, that reasonable provisions have been made. And this allows, although it's a standard approach, it allows that development, that innovation. So, I'm going to leave you, before I hand over to Paul, on the choice. The choice that we have is, do we follow, again, the big pressure in Germany from the manufacturers to implement prescriptive regulations that explicitly describe the methods, characteristics, materials, etc.? Or do we leave it wide open and say, go and design a turbine and make sure it's this safe and so on? I would suggest that there's something in between, a halfway house. Goal-based standards but that we as a sector, as an industry, ensure that we supply the certification authorities, the fabricators, the designers, all the stakeholders with the best information about our materials performance, the best models we can about the structural degradation process, the best inspection methods. And from that, to empower our best engineers and our best commercial people to pull together the best solutions. So that's it. I'm going to hand over to Paul now.
Thank you, Fergus. So we will take questions at the end with Julie, but for now, Paul, please.
Okay, thank you. I'll speak from here.
Right.
Okay, thanks. What I'm going to talk about is mainly based on offshore wind. However, all that I say is most probably largely applicable to any major infrastructure projects. So although it's focused on offshore wind, it will be very similar because there are similar issues across the piece. And typically, planning permissions, I think, are more difficult and trickier than permitting. It's in the planning that you get the political, and it's when you come to the permitting, it's usually just technical. And there will either be a technical solution or there won't be a technical solution. Whereas in the planning, then you have some other interesting debates to be had. So offshore wind is, as you will all know, covered by and underpinned by a national policy statement. Now, the importance of a national policy statement is that you have a single discussion up front as to whether or not that particular type of development is appropriate or not appropriate. It goes out to consultation, and then when you come to the decision and discussion about a particular project, you're not talking about the principles, you're just talking about locational issues. And that then means that if we just think about how long Sizewell B took, 10 years or so, because people were talking about nuclear power, Hinkley, because it's covered by a national policy statement, will go ahead very quickly once the decision is made. And it becomes a funding issue and a technical issue, not a policy issue around do people want nuclear power or not. And it's the same here. It's not a discussion about is offshore wind a good thing or a bad thing. That's been decided within the national policy statement. But within the national policy statement, it will also include a list of the issues that need to be taken into account, in particular, for that type of development. And what we then see is that then gets covered by what is called a development consent process. Now, once you put your application in, the development consent process should trundle along within a carefully designated timescale. And the whole thing is, the timescales are listed here. And you can see that once your application's in, then it's all done in a timely process. However, the pre-application process could take 5 years for people who've been involved in this process, or maybe even longer in some cases. So that pre-application process is vital. There is the thing called the Rochdale envelope as well. This is key, because what people are saying in this situation is you won't necessarily know when you start into the process exactly what you are designing. However, you should know general bounds within which you're going to operate. And then what you need to do is make sure that you include up to and including a potential cautious worst case. So that's what you need to do, so that when you're then looking at environmental impacts and any other impact studies, you have got the top end of the credible cases that you're going to be looking at. And then if you do all of your impact assessments based on that credible worst case, then you've dealt with everything that you need to deal with. And then as more information becomes available, then you provide that in and you gradually narrow down the process. It's clear, flexibility should not be abused. And this is one of the things that needs to happen within this pre-application process. And the pre-application process is most probably the most important time in any major infrastructure project. Within that, the planning inspectorate are key. And the title that I gave this was Talking to the Right People About the Right Things. So when you're thinking about it, they produce some really good information. So there is a prospectus. I mean, in that pre-application prospectus, it will tell you about what the planning issues are. It also tells you about what the permitting issues are. It takes you through the process. However, just phone them up and go and talk to them. Establish a relationship with the people who are actually going to determine the permit, the planning application. And when you come to the people in the Environment Agency or Natural England or SEPA or whoever it happens to be that you're dealing with, go and talk to them. And it's just very simple. They are just people. And too often, the things that I've seen is that this is all done by correspondence. And people have never just gone and talked to somebody and said, what do you want? And go and have that conversation, and it is incredible how helpful people will actually be in this process and guide you through it. Because the last thing that the planning inspectorate or the regulators want is bad information coming into them that they then have to wade their way through to then come back with, couldn't you have done better? So just have conversations. There was nothing else that I said today. It is just go and have conversations with the people who are going to be involved in this. Within the planning inspectorate, they've also designated leads for particular technologies. So again, go and talk to the person who is the technical lead, not just the person who's going to be involved in determining your particular application, but who is the subject matter specialist, and become their best friend. And they will respond well, I know. But that's, and then the other thing is that you need to have effective engagement just with all the stakeholders, local councils, local communities, NGOs, anybody who's going to comment on your application. You just need to go and talk to them. Find out what the issues are, discuss those issues with them. You might not necessarily agree with them. Listen to what they say, listen to their arguments, and then provide a coherent response in your documentation to all of the issues that have been raised with you. Because one of the things that the planning inspectorate will do when they are deciding whether or not to accept your application in the first place is just do a very quick read across and find out whether or not you've spoken to people. If you haven't spoken to people, they'll say, thank you very much, and that lorry load of documentation that you've sent through to us, well, just take it all back. So engagement around this process is hugely important. Also, as you're developing your documentation and as you're developing your draft development consent order, put that in. See what people think about it as you're going through the drafts. Now, under the Rochdale envelope, you will go through stages as you're defining the project. At each of those stages, draft a development consent order and submit it to the people who are going to read it in scoping, so that they are able to inform you about whether you're on the right track or not on the right track. It will save a lot of time and efforts. And you need to make sure that you've agreed as much as possible before your formal submission. If you've got a whole lot of outstanding issues and there's a lot of antagonism towards your proposal, then the determination will not necessarily go smoothly. So really, this pre-application period is crucial. Also, you then need to actively manage this process. It is in your interest. So you warn people before you send the documents. You tell them they will be coming in a couple of weeks. You might even say, can you designate some time? So that they know that they're going to receive something and are able to act on it. Also, you just need to be writing and communicating around these projects in a way that is understandable to the communities in which you're trying to get this through. And sometimes it's just good to get other people to read some of what you've written, honestly. And non-experts, your families. And just give it to your families who might be just educated but not detailed knowledge experts, and get them to read it and see whether or not they understand it. Then think about that could be going in before a planning committee or local councillors. That's the level at which this needs to be understood. You'll also need the technical information, but you do need versions which are readily understandable. We'll come to this because there was a comment made by Renewables UK in which they said government agencies have been cut back and lack the resources and the skilled workforce required to speed up approvals. Now, I don't believe that statement. And anyway, one of the ways that you can get round that is that through the pre-application process, it is possible to fund the government agencies. So if you think about what the total cost would be to fund people within those agencies to do this work according to your timescales, in terms of the overall project costs, the cost to fund those people is trivial and is hugely important. So if you just think about some work that I was involved in on the Olympics. The Olympic ODA, the development folks for the Olympics, paid for 7 people from the Environment Agency at any one time. 3 core people, and then the ability to bring in other technical specialists as need be. Crossrail has done exactly the same thing. Terminal 5 did the same thing. High Speed 2 is just going to fund a team of 10 people. And they're doing exactly the same with Natural England. So in terms of development, low cost, but it does help to de-risk and make sure that you're getting timely responses to any questions that you raise. So it's your process. You're the people who are most interested in getting that through. So actively manage the process. The other thing is that it's quality, not quantity. If you send 3 wheelbarrow loads of information and it takes the person delivering the information to the planning inspectorate 5 minutes to bring in all the boxes of information that you've provided, they will have to read it all. And they will read it all, and that just makes the whole process longer. So this is about quality of information and layering the levels of the information and giving confidence that the information that you've provided is of the right quality. And it is surprising how poor some submissions are, even for large projects. So this is all about quality, not quantity. most planning, safety and environmental risks in offshore wind are in the early development phases. That's what and so therefore you need to think about what all of those risks are going to be and then to manage them out. And there is considerable expenditure on schemes which are never built, never get past the planning. Here we have some of the statements from Renewables UK. Round 3 projects will take up to 5 years to get approved. Now, the approval process itself is most probably just about a year and a bit. It's that pre-application period which is taking most of this time. And development period to full operation is about 10 years, which is a significant period of time. I think you can manage that government agency's risk, and that's for you as businesses to manage. I just put this up because it's interesting. This is an approach that the Danes have taken. And I have a lot of sympathy with this. And it's interestingly, the first place that I came across this was in Lancashire. Lancashire, not in Denmark, Lancashire in northern England. And they did it with their waste infrastructure. And in their waste infrastructure, the county council identified locations, got the planning in place for those locations, said what technology they wanted, and then on the basis of a location with planning permission, then went out and asked for tenders to operate, to build and then operate a plant. The Danes have done exactly the same. They have identified where they want the offshore wind to be. They then got their government agencies to do the environmental impact assessments and any other assessments that need to be. They've designated the number of turbines or the generating power that they would like from a particular location. And then on the basis of that information, they've gone out to tender for a design and construct. That de-risks the whole project. It then means that if you've de-risked the project, then your financing costs, and as Fergal was showing, significant financing costs are to do with the risks. Well, take the risk out, which is this project is going to go ahead, then you reduce the cost of capital. Then you reduce the cost of electricity. Then you become more competitive. So you get rid of nugatory planning and development costs, and you reduce the cost of the overall project. Now, interestingly, the Dutch are also going this way. They've had a look at it and have decided that this is the way that they'll go forward. I think there's something in the UK that needs to have a look at this type of approach. It'll be a sort of national planning statement plus. Now, whether government will go that way is to be discussed, but I think it certainly is something that's worth looking at. David.
Cool. Thank you, Paul. And I want to start really with an apology for dragging us into the dirty world of litigation. But there will be a Q&A and, more importantly, wine afterwards to relighten the mood. I'm going to talk about a recent case which arose in the offshore wind sector, and it's one that Fergal trailed on his slides earlier. It involves MT Hoggard and E.ON, and it was recently referred to the Court of Appeal, and it throws up a whole number of issues which are interesting from both an engineering and a legal perspective. The case, as many of you will know, concerned offshore wind turbines in Solway Firth in Scotland. They were known as the Robin Rig East and Robin Rig West turbines. And I'll make the engineers wince with my lawyer's description of the technical background. So you have a monopile driven into the seabed, then a transition piece which sits on top, and then the tower slots into the transition piece. And the monopile and the transition piece are bonded together with with grouts, and that's illustrated on the diagram here. So you see on the right-hand side the grouted connection, which works by friction between the layer of grout and the two steel surfaces between which it sits. And it's that grouted bond which has to withstand the downward pressure of the tower on top. Is that just about right?
Yeah. So, assuming you don't have a stopper plate in the way.
Thank you. So in 2004, there was an international standard published, which was known as J101, and that standard related to the design of offshore wind turbine structures. And section B includes a series of parametric equations. And there was an equation on the slide there, which I won't attempt to explain because I can't, but in essence, what it does is it states the strength of the grouted bond. However, and as we'll see in a moment, it transpired that there was an error in the equation, and in simple terms, the effect of that error was to lead the designer to overestimate the strength of his foundation by quite a margin. I think somewhere in the region of a factor of 10. So a fairly significant problem. So in the Hogarth case, the contract imposed a variety of obligations on the contractor, both in the front-end terms and conditions and scattered throughout the numerous technical appendices. And I've reproduced three which are at the centre of the Court of Appeal's reasoning on the slide here. And on the left-hand side, we see obligations which look absolute in nature. So, and in particular, the requirement in the TRs, the technical requirements to ensure foundations with a 20-year life. And on the right-hand side of the table, you see obligations to comply with standards and good industry practice. And there's a tension between the two because compliance with standards and good industry practice doesn't mandate an outcome, whereas the obligations on the left of the side certainly purport to do so. And really, it was the tension between the right and the left of the table which was at the heart of this particular dispute. So what happened in practice? The contractor designed in accordance with J101, and he received foundation design conformity statements by the third-party certifier. And in February 2009, the works were completed. Then in September 2009, a grouted connection on a wind turbine elsewhere in the North, I think in the North Sea, failed, and that caused the DNV, who produced the standard, to look into what the issue was, and it's there that the error was identified, and this affected a number of projects in the North Sea at the time, Hogarth being, I think, the only one which has been subject to the scrutiny of the court. In April 2010, the grouted connection on the Robin rig turbine started to fail, and remedial works were carried out at a cost of around about 26 million euros, and there was then a dispute as to who would bear the costs of the works. The case went to the Technology and Construction Court in the first instance, and the trial judge found in favour of the employer, and he did so by relying quite heavily on, if I skip back to it, the top obligation in the left-hand side of the table, so the one that purports to be a 20-year warranty, so that a guarantee that the foundations will in fact last for 20 years. Case went off to the Court of Appeal. The Court of Appeal, at the start of quite a punchy judgment, ran through some of the general principles of interpretation, and they said that as a matter of principle, a contract can impose what they called a double obligation. So that's an obligation on the one hand to comply with standards and good practice, and on the other hand, an obligation to ensure a guaranteed outcome. And if the contract is drafted sufficiently clearly, then the contractor will have to comply with both, even if guaranteeing the outcome involves going above and beyond the standards, so going what the court called the extra mile. The court also noted at the start of its judgment the length of the contract and the voluminous nature of the technical appendices in particular, which I think is actually an important feature of how they got to their decision, which I'll come back to shortly. So the Court of Appeal said that yes, the technical requirements did look on their face as if they were imposing a guarantee that the foundations would in fact last for 20 years. However, that was inconsistent with the rest of the contractual scheme, because the rest of the contractual scheme was centred around standards and obligations which were tied back to good industry practice. The court also considered obligations to achieve a 20-year design life, and the court drew a distinction between an obligation to guarantee a 20-year life and an obligation to ensure a 20-year design life, and the two are not the same. The court's view was that to achieve a 20-year design life, you do what standards and good industry practice tells you is required to be done to have a structure with a sufficiently high probability of actually standing for 20 years. But it doesn't guarantee that it will in fact stand for 20 years. And the court was influenced by the fact that the standards are stochastic. They're based on statistics, they're based on a series of assumptions, and in any given year, a structure can be subject to far greater loads than are assumed in some of the parametric equations in J101. The court held ultimately that. The court held ultimately that the contractual scheme as a whole was tied to good industry practice and it was tied to standards, and that in effect overrode this what the court saw as an anomalous statement tucked away in the technical requirements that the foundations would in fact achieve a guaranteed 20-year life. And the court was influenced by the argument made by the contractor that had that been a central term, it would have appeared prominently in the front end terms and conditions. It wouldn't have been tucked away in the technical requirements. I think that's where the court was influenced by the length of the contract and the complexity of the document, and why it was willing to highlight one term which looks fairly clear on its face as being anomalous and therefore inconsistent with the scheme, and therefore not an obligation that qualifies the obligation here to use standards and to achieve good industry practice. And the court held that by designing in accordance with the standards as they then stood, notwithstanding that there was a fairly substantial error in those standards, the obligation to meet good industry practice had been satisfied. So when it was turning to its conclusions, the court just felt that one clause was, its words were too slender a thread. But it's clearly a finely balanced argument, which is why you have two very respected judges, one in the Technology and Construction Court and one in the Court of Appeal, jumping different sides. I don't know if there is going to be a further appeal in this case, but if there is, then it's quite possible that the Supreme Court may jump back again or may jump a third way. So it gave rise to very difficult, complex points of contractual interpretation, and ultimately they come down to the views of the judge on the day. But the key lesson I take from this is making sure that the contract is clear, and in particular, if you want to impose an obligation on a contractor to go above and beyond good industry practice and to go above and beyond what the standards say, you need to do so sufficiently prominently. The Technology and Construction Court thought the employer had done so. The Court of Appeal disagreed. It's fine balances, but you are best served by making sure that that obligation is as prominent as it can possibly be, rather than burying it in a technical schedule. So with that, I will hand over on a lighter note, hopefully, to Julie for the Q&A.
Thank you, David. Great. So this is the part of the proceedings where you get to raise all those burning questions that you've hopefully occurred to you as we've gone through three very interesting presentations. I'm sure you'll agree. I think to sum up, Fergal has led us from the dinosaurs and via floating turbines in the land of the sun, conjuring up lots of images along the way, and about VW's emissions and how we're all going to be moving to electric cars, for example, and making the problem potentially worse in terms of emissions. And he's led us to understand, I think, the gap between cost avoidance at the one end of the spectrum and over-designing our engineering solutions at the other, and raise the dichotomy in terms of regulation between setting prescriptive standards or, on the other hand, a goal-setting approach, allowing people to go off and innovate. Paul has explained to us the DCO, as we like to call it, Development Consent Order process, and I think he's urged us to be best friends with the regulators and to leave those wheelbarrows of documents behind, much to the disappointment of the lawyers in the room. It's also encouraged us to pay their wages, which was, I thought was an interesting stance. David, however, has interestingly for a lawyer, waved a sort of mystical equation in front of us, which I have no clue what it does, David, but I'm sure some people in the room probably do. To me, it looks straight out of Hogwarts, but... And then, of course, you've made the engineers wince with your description of the engineering, but then gave us a very lucid explanation of the recent Court of Appeal case. So thank you very much. So over to the floor. Would anybody like to raise the first question? Gentleman at the front.
Hiya, yeah. The question for Paul, really. When you were talking about the Rochdale envelope, it reminded me of an experience that I'd had on a project where it was to do with environmental impact coming out of submitted documents, and we were kind of asked to look at effectively the bird mashing potential of having the biggest turbines at the closest spacing. And it was sort of, it was an engineering question of something which could never happen. I'm guessing that was probably an omission in our submission, that we hadn't been careful enough about identifying the small turbines and you've got more of them, or you've got the big ones and you've got fewer of them. But can you shed any light on how that can be rationalised?
Well, I think that in that situation, if that is not a credible configuration, then that question shouldn't be asked. And you just then need to know. I was talking to my son about this, who was involved in, from the other side on DCO, and we were talking about how far will you get agreement from regulators, and when do you have to push back. And and again, that comes to this bit about talking to the right people about the right things. It would be, who is the right person within the array of regulators and planning inspectorate that you're talking to, who should be considering that as an issue. And sometimes some regulators will bring up issues which are not within their remit to bring up anyway, in which case you go, it's nothing to do with you. And you need to be very firm with those ones, which is, this is nothing to do with you. And so in the case of my son, it was, somebody was raising an issue which was to do with another regulatory body, and in the end they just told that person, you know, we're not answering your questions anymore because actually they've got nothing to do with you. So that's the first thing. Are you talking to the right person about that? But the whole thing about the Rochdale envelope is, if that is not a credible position, then you don't need to consider it. And again, you would go back to those people and say, this is not going to happen. It is a hypothetical. You might be interested in it. If you are interested in it, then go and talk to some university about an R&D project, but it's not a credible issue.
Mm-hmm. Thank you, Paul. In the middle.
Guy Grant from the National Centre for Atmospheric Science. A quarter of a century ago, when I was an aerospace engineering undergraduate, I was taught wind turbine design as a special case variation on helicopters, which made me look with great interest at Fergal's description of general versus specific, what one might call weights and measures standard setting, which did look very much like the dichotomy that exists within airworthiness legislation, where there are baseline standards, Part 25 for airliners and so on and so forth, and then there is a whole raft of documentation that sits behind it called acceptable means of compliance, where if you are a very clever, very able company, then you can actually reinvent the wheel, you can use your own best science to interpret the general requirements, or if you're not just want to get it done, you can go to the AMC and simply work to that. Has anybody had a go at cross-referencing the approach that's being migrated towards on the offshore energy generation to the way that we practice in airworthiness?
Yeah, I'll take that. The answer is no. Nobody has done, but I think it's hugely important, and part of tonight airing some of these issues, hopefully we'll get some momentum going on this. I'm chairing a session in Paris at the EWEA in a few weeks' time, and it's essentially to try to get that type of study started, because there are fundamental differences in terms of culture. When I take aerospace in general have deep specialists. Obviously, it is a safety critical application, and so we've got a different. We did have a different level of technical competence within aerospace compared to power gen. Now, if I take power gen, traditional power generation, apart from the specialist nuclear power people and so on, but the run-of-the-mill coal fires, gas fire stuff, you know, it doesn't or hasn't required from a competitive perspective, technical innovation. It was really about the cost and supply and so on of the fuel itself and the logistics, but it's really based on the commodity rather than the technology itself. What has been truly impressive to me has been these conventional companies, and I will call the Eons and the EDFs and the Centricas and so on true pioneers, RWE and so on, pioneers that they have gone out of their comfort zone and, without a whole lot of encouragement from governments and so on, to have gotten involved in something maybe they didn't know what they're getting involved in. But if I'm to compare, a 5 megawatt wind turbine compared to an Airbus A380 in terms of size, the diameter of a 5 megawatt wind turbine is 120 meters. The wingspan of an Airbus A380 is 60. So the other thing that you're doing is you're rotating this thing. So it's truly phenomenal. And I think there is that balance. And I think there is, but it's something new, because I think this whole, to design something and to build something for just as good as it needs to be is very important. The other aspect, the other dimension that we're looking at here is we're designing power stations. We're not designing aircraft. And the most important thing that we can gain from that is things like reliability and maintenance. It's far more important than the subtleties of aerodynamic efficiency. So very, very good analogy, and I think benchmarking across the development of new technologies. But I think what we need to be able to do is to learn from those lessons of rapidly developing and implementing new technologies, but getting the cost right.
Perhaps just following on that one further, I think it lies slightly between yourself and David. I was going to ask about the maintainability, but you just sort of highlighted that. But I suppose just going one step on, if you think about the way in which the aerospace sector has moved from the Capex and Opex type model through to fly-by-hour and what have you, and making a loss on the capital expenditure and through the sophisticated use of lifetime predictions, do you think in the offshore renewables that you're going to see that same transition as business model going forward, or not?
Absolutely, absolutely. Andrew Garrett last week at Cranfield. Those of you who aren't familiar with Andrew Garrett, he set up Garrett Hassan, the world's largest wind power consultancy, sold it on to Jaman Lloyd, and in turn was bought by DNV. He exited from that a few years ago, so he's now free. So he was able to come, he came to Cranfield, and he was, in his presentation, he showed pictures of the Pope, and he showed pictures of Angela Merkel, and along with Amber Rudd. So it was very entertaining, but he was free from the shackles of, I suppose, the establishment and having to say the right thing. He left us with one message. And that was that in order to get this right, we have to change. We have to be innovative, not in the technology, but in our financial models. And that is so important. We're seeing it in oil and gas. And we're seeing it after the first generation of operators have exited. And now, who operate our oil and gas platforms in the North Sea? Talisman. Who knows Talisman? We've got Petrofac. So they have come in and they've said, righto, look at these assets, worth £1 billion or so, and let me try and maintain these and run them and extend their life for things that were initially designed for 20 years. But if I'm designing or conceiving of a hydroelectric power station, I'm going to design that for, or I want it to go for 100 years or 150 years. Maybe I'll change things out. So I think you're dead right, Peter. I think the innovation that we need to see is, yes, the technology, but a lot more on the commercial and economic elements as well.
Mm-hmm. Back.
You mentioned before that we're now fast evolving industry.
Yeah.
10 years ago, nobody had an idea of what it would be now. But changing standards takes quite a long time. So how we can change the standards to be more accurate?
This is important, and the stuff that David showed. The DNV standard was wrong. Yeah, why was it wrong? And lots of people a few years ago said, "Look, who are these DNV guys?" DNV don't have a fund. They don't have a crystal ball. They don't know what developers are thinking of doing in 10 years' time. The standard was wrong. The equation was wrong, David. Why? Because the tests were all done on small diameter grouted components, whereas the biggest test that was ever done was on 500 millimeters. Whereas what are people installing today? 8-meter diameter, from here to there, and this wall thickness. So we can't extrapolate those things. So how is it done? It's done by consensus. So standards themselves, if we can get, and from the Carbon Trust, for example, that you represent, and others, DEC, and there's various other initiatives, ORE Catapult, I don't think there's an ORE Cat person here, they could do what the Department of Energy did in the 1970s, 1980s, and they convened, you are doing this on suction buckets and so on, convening a pan-industry to get around the table. This is not competitive stuff. And in terms of agreement, get the best brains, intellectual minds around the world, fire it out there for peer review, and we will get there. And it is through that rigorous process, it doesn't need time. What it does need is a willingness, it needs absolute transparency, and we need champions, people to drive this through, and personalities to be able to bring together all the stakeholders. And I think we will see, you are aware of the SLIC program that we're dealing with, 18 months. 18 months, we reckon we're going to have new design curves because we've got the industry all together.
I think it's also an important point when it comes to looking at the types of obligations you put into the contractual documents, because when you're dealing with a sector where standards are still developing, if you want to impose on the contractor any sort of fitness for purpose obligation, you're effectively asking the contractor to take the risk that the standards as they currently exist are adequate and that good industry practice is adequate. And that has if a contractor is willing to take that risk, it has a significant price impact, which brings us back to the upfront Capex point.
Yeah, Diego Campos, Ferrovia. You mentioned Paul earlier the Danish approach, and here in the rest of the countries in Europe, how far are we from the state or the government taking an area and giving the developer, then go ahead, that's it, you can work there. I was not directly involved in the Navitus project, but indirectly, and I find it frustrating for so many contractors and so many people trying to make that project go ahead. And all this time, all this energy, all this money that has been spent, and it actually, if I understand well, it's going nowhere right now. And that could have been spent differently in innovation, in improving other technologies and doing things much better. How far are we from there, from the state? Like you can see that in motorways saying motorway has to go through there, and it will go through there because I say so. How far are we from there?
Quite a long way in this country, because the whole thing in this country is that most planning matters, apart from DCOs, but even with the DCO, the local authority is involved to an extent, certainly for associated development. But I think that the Danish model is an interesting one and is worth having a look at. I think one of the things that needs to be done on it is to actually work out what the cost savings are. Because if you can demonstrate the business case and then think about how you would submit that case to the Infrastructure Commission when that gets established, and then you can get the politicians to think that is a good way of doing it, then that has to be the way. Just now, it's only the Danish who are doing it, although, the Dutch are now following on. I think if you could demonstrate significant cost savings, there would be a real advantage. I think one of the interesting things with the Navitas one is, and I was just mulling this over, which is, if you did some initial, I mean, one of the things that Fergal was saying was that usually offshore wind is sort of out of sight, out of mind, and therefore planning isn't an issue. Usually if you go onto the East Coast, they're away in the distance and you can just about see them. If you were stood on the Jurassic coast, it would be interesting to see how visible Navitas was. And if it was that visible, why did people go ahead? Because there was a sort of scoping issue that sort of should have been thought about. And at that scoping level, that's why I think the pre-consultation is so important. Right at that scoping level, talking to the local communities about it would have got most of these issues before people had invested so much money. So I think that initial scoping, thinking about it, what are going to be the impacts, rather than people going with, we've got a really good technical solution here, and not thinking about the social issues associated with that, needs to be considered. Because it's hugely frustrating.
David, I'm just interested in your thoughts in terms of contracting. The traditional sort of EPCI contract is almost a battle between the clients and the contractor, in the sense that as the client, you write your specification to deliver the best product that you can get, and you give that to the contractor who therefore wants to deliver the specification for the least amount of money. And often a product gets produced at the end of it. In a case where there's a failure, then we all go back to the contract and we go through whose fault is this. But there's quite a clear divide between the client and the contractor. Whereas if you try and merge that together a bit, to work better together to try and get to whatever the answer is, you might it has the potential to work, but if it goes wrong, where does that leave you in a contractual sense?
Yeah, I think it's a really good point, because I think a large number of the disputes I've worked on have arisen out of disagreements over the specification in particular, where the contractor feels that it's operating under in a straitjacket and that it wants to deliver something different, and it looks for ways around that, and that tends to be when you get into claims territory. So a number of sectors have moved away from that, and they've gone for sort of various different models of early contractor involvement, where you involve the contractors up front in developing the specification effectively during the tender process. So you may work with two or more. The theory being that the contractor gets the specification he's willing to build, and the employer knows the end product that he's actually going to get. Partly that is then typically rolled up into your traditional sort of adversarial type contract model. So in theory, the employer has to instruct any changes and will bear the time and cost consequences of those changes. But equally, the contractor is bound to deliver that product. But because you've done that work up front, disputes are less likely to arise. One of the things I'm quite interested in is to see how much traction NEC gets in the offshore sector, because that provides for a more collaborative approach during the life of the project, and you have typically a greater dialogue between the employer and the contractor throughout after contract award, and it's been extremely effective in other sectors at reducing disputes. So pretty much any big publicly procured dispute at the moment is under NEC3, and there haven't been any big fallings out. The Olympics was NEC3, Crossrail is NEC3. There's nothing in the courts. It's delivering huge projects without disputes, and I think because it encourages the parties to encounter issues as they come, deal with them then, and move on to the next one. So you've got a revolving door. You don't have your sort of final account wash-up, which is when sort of the gloves come off at the end of the day. And that's been a very effective contracting model, and I think it has been used for some offshore wind projects. And I think it could potentially has a lot to offer, because you do get problems out of the way and you move on, and you don't bottle things up until they become so big that a dispute is really the only way to unlock the parties' positions.
I think that it was interesting because we went through that transition on flood risk management and procuring in that, and moving from frameworks and then potentially from frameworks through to alliancing, which becomes even closer. And how do you then have pain and gain share within that? So that all gets locked in. And I remember, many years ago, it was with some construction companies, they most probably had as many lawyers as they did engineers, because that was where they made their money.
Yeah.
Post-contracts, litigation. Now, as you say, and we had some big disputes, huge disputes, took up huge amounts of time. Now, in the Environment Agency, they wouldn't have those disputes. But I think, if I can just ask a question, which is, what are the implications of that judgment on the reliance of certificates of conformance, asking for a process, certification? It looks like the contract isn't worth a lot unless you specify that in big letters.
Yeah, it's a particularly stark example because the error in the standard was so significant. Had it failed after 19 years into its 20-year design life, no one would have really batted an eyelid. But when it starts to effectively fail on day one, you look at it and it does look quite stark. I think that the implication it has is that if you don't make your overriding fitness for purpose type warranty, assuming that's what you've negotiated prominent enough, your protection is all around the process, if you like, that has led to the design and that has led to the what is in fact delivered on site, rather than the end product. I think that's the implication, and that's where, particularly in an area where standards are to an extent developing, it's a judgment that could have wider implications. Yeah. Albeit, I would hope they won't be as stark as this case, where you had a serious failure just over 1 year into the operational life.
Okay, I think possibly two more questions. You've had your hand up for a while. So.
Very brief, and it relates to the topic we were just discussing. But as a lawyer, further, what's your reaction from an industry perspective to a performance guarantee for 20 years? Because the Court of Appeal is obviously very uncomfortable with that. It's found a way to reason around it. What's your reaction from an industry perspective?
Guarantee, as a lawyer, you'll be familiar with the word reasonable. But it comes to what I said before is competence, is using the best knowledge, the wherewithal that's available at that time to put together, to bring all of these things together, to demonstrate as well as possible that we can quantify our certainty or uncertainty, this will last for this period of time. Obviously, there will be caveats and so on, but we know how to do that. So I don't have a problem. I think, obviously, the guarantee word can be pretty solid. Nothing is absolute. And I think, if it is worded properly in terms of, to use best endeavours and to be able to demonstrate a competent and capable process, I wouldn't see a difficulty with that.
Okay. So,
Techie question for Fergal. And you mentioned, and it was kind of discussed briefly from the Carbon Trust guy there, that there needs to be research done to develop standards.
Yeah.
Where does the research need to be done?
There's two levels. One level is the longer horizon stuff. So when I mentioned about the floating things, this is around the corner. It's happening. We know it is happening. So that is still at the concept level. The nearer stuff and the more immediate applied stuff goes back to points that Peter alludes to, and that is understanding maintenance and the cost of maintenance reducing costs, remembering that offshore, every operation I do is 10 times more expensive than that equivalent operation onshore. The first generation of wind turbines that have been installed assumed practically no maintenance costs, or we visit these things once a year. We're currently visiting them every month. What we haven't yet done is avail of the tremendous advantages in sensor technologies, structural health monitoring, information, data fusion or information fusion. And it's to manage systems. So what we have done so far is we understand the individual turbine. We don't understand the array. We don't understand the wake effects. We don't understand, by getting this information from here, what can we tell about from a diagnostic and a prognostic perspective in what intervention might be or might not be needed. So I think there's an awful lot of stuff that is possible and could reap benefits very, very quickly in a relatively short period of time. The integration of sensors, sensor technologies, with an understanding of damage modelling and so on. But then in terms of the longer term stuff, it's the thinking outside the box to say, righto, we're going offshore. What can we do offshore that we couldn't have conceived of doing onshore? And from an engineering perspective, we can do lots of things offshore that are not possible onshore. We can lift thousands of tons because we can use water as a ballast. So anything we do onshore, the largest lift I can do is a few hundred tons. Yeah. So it's really going that step further. So my prediction is that yes, we will have wind turbines in 20 years' time, and in 50 years' time, I guarantee you they won't look like the ones that we have today.
So, thank you very much for all the questions and engaging with all the speakers, and I'm glad to see that, as usual, we have a lot of very sort of insightful questions coming from the floor. We're going to have some wine and canapes and stuff, which I'd encourage you all to stay for and ask any further questions that you didn't that I didn't spot to you for this evening, to place those with the speakers afterwards. But first, before we do that, I'd like you, if you wouldn't mind, to put your hands together and thank the speakers this evening. You'll notice on the board, I think, that last advert there for our next event, which is at Cranfield in January. Thank you very much for coming.